Good evening. Welcome to Science of Sleep. If your day has hurried past like a gust of busy wind, or if it has drifted by in unhurried quiet, I'm glad you have anchored here tonight. Before we cast off into the ocean's secret highways, please consider tapping the like button and subscribing to Science of Sleep so you will always have a calm harbor for curiosity. And now, a gentle favor. Where are you watching us from, and what time is it there right now? I love seeing how far these nighttime explorations travel across the turning earth. Take a slow, comfortable breath. Feel the air rise through your chest like a tide climbing moonlit sand. Then exhale with the ease of waves slipping back to sea. That measured rhythm is your proper time, your personal compass, as we descend beneath the waves in search of the hidden rivers that govern heat, storms, and seasons all around the globe. Picture yourself alone on a wide shore just before sunrise. The horizon blushes, rose and tangerine, while a hush nestles between the murmured lap of waves. Cool sand gathers between your toes, and a salt-sweet breeze tastes faintly of seaweed and distant rain. Beneath those trembling ripples lies a vast, unseen web of currents, some warm as midsummer light, some cold enough to numb bone, all gliding in patient loops that connect equator to pole and back again. They shift clouds, coax rains, feed plankton blooms visible from space, and decide whether winter wheat ripens or wilts thousands of miles inland. Our journey begins near the equator, where sunlight descends nearly overhead. There, the oceans. Skin drinks an immense blaze of energy. Water molecules jiggle apart, and the surface swells by a few silent centimeters, enough to start a long, slow slide away from the glowing belt, toward cooler latitudes. Trade winds push from behind, while the turning earth nudges from the side. That sideways nudge is the Coriolis effect, a subtle guide that deflects moving water to the right in the northern hemisphere, and to the left in the southern. Imagine sliding a puck across a giant spinning carousel. No matter how straight your push, the puck curves outward. Over thousands of miles, these forces sculpt grand spirals, called gyres clockwise in the north, counterclockwise in the south, each broader than a continent and deeper than mountain roots. One gyre is the North Atlantic's mighty swirl, whose warmest limb bears a famous name, the Gulf Stream. Born in the Caribbean's turquoise cradle, it slips through the tight strait beside Florida like a river pressing through stone gates, then sprints northward along North America's coast. Satellite images capture the Gulf Stream as a fiery ribbon, amber, copper, gold, looping and relooping, shedding eddies that spin like sparks falling from a welder's torch. Inside its sinuous channel, tropical water carries the memory of blazing sunlight toward the chill latitudes of Europe. That warmth, delivered day after day, tempers winters that would otherwise feel arctic. London and Calgary rest on similar latitudes, yet London's coldest nights hover just above freezing, while Calgary's plunge far below zero. Contrast written by an invisible current beneath the Atlantic, as Gulf Stream waters give their heat to the air. They cool, grow denser, and eventually plunge toward the seafloor near Iceland and Greenland. This descent is the first step of a planetary conveyor belt scientists call thermohaline circulation, thermo for heat, halon for salt. Picture an endless escalator vanishing beneath a grand floor, traveling through hushed corridors, and rising again oceans away. Cold, heavy water sinks, slides southward along the abyss, skirts submarine canyons, and centuries later rises in far-off domains, like the Antarctic circumpolar current or the upwelling zones of the eastern Pacific. The water you see sparkling in a crest near Miami could one day emerge beside an emperor penguin. Rookery under a sky of circling albatross. Allow your shoulders to loosen, and with your next breath feel tension drift away like foam carried off by gentle backwash. That single invitation breath, release glide mirrors the ocean's patient pulse. Surface currents move heat. Deep currents vary breath itself. As dense water sinks, it drags dissolved oxygen into black hollows, where creatures with translucent shells and lantern organs hang in the stillness. Those same waters also hoard carbon exhaled by forests, cities, and your own lungs. Part of that carbon will remain hidden longer than stone monuments endure, while another part will return with future upwellings, to fuel new blooms of microscopic plants. These phytoplankton, tinier than dust motes, weave carbon and sunlight into sugars, feeding krill, fish, whales, and ultimately us. When phytoplankton die, their bodies clump into marine snow, drifting downward like a slow blizzard toward darkness. In this quiet snowfall, the ocean buries yesterday's breath, moderating the climate in ways most of us never feel, but all of us depend on. Now imagine tilting a shallow sheet of honey on a warm stove. The glowing top layer softens and spreads, pushed by the faintest tilt, until slow rivulets trace wandering paths. Trade winds serve as that tilt, sliding Caribbean warmth northward, while Earth's rotation curves the flow eastward across the Atlantic. The result is a conveyor that acts like a global radiator, carrying 800 times more heat than the atmosphere can hold. Without this moving warmth, the temperate zones would shrink, deserts would sprawl, and ice would encroach on farmland where wheat fields now wave. Currents do more than transport temperature. They choreograph rainfall and drought, shape hurricanes, and define the edges of fog belts. Over warm stripes of surface water, evaporation intensifies, loading air with moisture that coalesces into towering thunderheads. Those clouds drift inland and break into rain that feeds forests from Ireland to Norway. In contrast, over cold currents like the Humboldt or the Benguela, air cools and moisture condenses into low-stratus blankets clouds that cloak coastlines, yet seldom break into showers. Farmers along Chile's Atacama Desert and Namibia's Skeleton coasts have learned to harvest this cloud-kissed air with nets that comb drinkable droplets from fog, all thanks to cold currents stirring offshore. Life follows these temperature signatures, where nutrient-rich deep water rises, plankton bloom, fish gather, seabirds wheel overhead, and human boats drift, nets poised. Off Peru, the Humboldt Current feeds anchovies by the trillion fish so numerous they darken the sea from turquoise to slate. Their abundance supports sea lion colonies, pelican rookeries, and fishing towns whose economies hinge on the cold, upwelling. Yet every few years, a warm tongue called El Niño glides eastward across the Pacific, smothering the Humboldt's chill breath. Anchovies vanish, seabirds abandon nests, and coastal fishers face empty holds. The chain from hidden current to village market is immediate and profound. Currents even sculpt culture and history. Vikings sailing west sensed warm water under their hulls and followed it toward North America. Spanish treasure fleets rode cold currents south of the Canary Islands to pick up favorable trades. Steamships later shaved weeks off transatlantic crossings by hitching rides on the Gulf Stream's swift heartbeat. Remote islands owe their cloud forests to moisture borne by currents. Coral atolls owe their bleaching and, sometimes their recovery, to pulses of unusually warm or cool flows. Pause to imagine a single drop of seawater resting now on your skin after a playful splash. That drop could, in its lifetime, journey from the equator's furnace to Antarctic twilight, sink under crushing weight, glide 1,000 years in darkness, then rise again to greet the sun. Your own heartbeat ticks more than 500 million times while that drop slumbers in the deep. The scale humbles and steadies the restless mind. Human instrument makers chase these wandering drops with ever finer tools. In the 18th century, navigators lowered thermometers in canvas buckets to chart surface temperatures on tall-masted voyages. In the 20th, glass drift bottles traveled currents, revealing secret lanes when waves delivered them to unexpected beaches. Today, an army of orange Argo floats dives 2,000 meters, drifts with deep currents, rises, and radios temperature and salinity stories to satellites. From those signals, scientists weave maps of the ocean's beating heart, maps fed into climate models that policymakers depend on when planning levees, harvest schedules, and carbon budgets. But measurement reveals warning as well as wonder. Greenland now sheds fresh water faster than any time in recorded memory. That lighter water spreads across the North Atlantic, diluting salinity and reducing density so less water sinks. When sinking falters, the conveyor slips. Ice cores show abrupt cooling events in Europe linked to earlier meltwater floods. Should a similar slowdown develop, winter frost may bite farmland unused to such severity, while tropical zones could see storms ricochet along new, unexpected tracks. Let your breath glide once more steady, effortless, patient. Know that somewhere, Beyond your walls a swirl of warm water slips northward, a plume of cold water creeps southward, and deep shadows cradle carbon that will rise someday to feed blooms yet unborn. These currents interlace planet and people, leaf and cloud, memory and future in one unbroken ribbon. Hold that image close. A planet whose gentlest breezes and fiercest storms alike begin with silent rivers beneath the sea. Their loops and whirls set the cadence for climates, govern migrations, and write the margins of civilizations. In our next steps we will sink deeper into the ocean's carbon ledger, examine its chemical balances, and meet the creatures that surf temperature fronts, like travelers on invisible roads, all without pausing the calm rhythm guiding us forward. Trace, if you will, the silhouette of Earth in your mind's eye, not as a globe spinning in empty black, but as a living blue engine whose slow pistons rise and fall through water. Down in the Atlantic's mid-latitude, mid-depths, colossal volumes of seawater slide south, chill, sink deeper still, and edge beneath the equator like shadowy freight trains. Their cargo is carbon, oxygen, and ancient memories of weather long since blown to dust. They pass rugged ridgelines where hydrothermal vents belch mineral-rich plumes, then sweep through basins so dark no starlight has ever slipped inside. No current flows in isolation. The one you are imagining links by invisible junctions to others in the Indian and Pacific Oceans, forming a planetary subway, so steady that continents drift while it stays on schedule. To understand what these shadow trains carry, let us hover for a moment at the water's surface in winter near the Labrador Sea. Wind howls off frozen tundra, stripping warmth from steel-gray waves until ice crystals cluster like tiny stars. As the surface cools, it grows dense salt content high, temperature low, then overturns violently, plunging great tongues of water down more than 2 miles. Oceanographers call this deep convection, a phrase that sounds delicate but masks a fury of mixing whose roar you could hear if your ears were tuned to the groan of collapsing water columns. What matters is that every gargantuan gulp drags atmospheric gases downward, oxygen for deep-sea life, carbon dioxide from fuels burned half a world away. A ledger entry against future warming. While that cold bolt sinks, a mirror image occurs at the other end of the world. In the Southern Ocean's turbulent circumpolar belt. There, relentless westerly winds whip the sea surface into white veils. Upwelling brings water last at the surface centuries ago. It is saturated with nutrients, phosphates, nitrates, silicates, dusty spoils collected from hydrothermal ridges and dissolving shells. When that nutrient soup meets sunlight, it detonates colossal blooms of phytoplankton. Seen from space, the blooms appear as jade and turquoise whirls swirling across thousands of square miles. Each cell is a single-celled alchemist, splicing carbon into sugar chains, splitting water to free oxygen, and building intricate glass houses from dissolved silica. Take a generous inhale, draw air deep, feel it fill every corner of your chest, and as you exhale, imagine loosing that breath into a microscopic forest of phytoplankton. Let any lingering tension slip out alongside the carbon your body no longer needs. That single, soothing breath echoes the quiet exchange that happens billions of times each second over the sea. Carbon out, oxygen in, balance restored. Blooms feed higher tiers of living gears. Krill swarmed beneath the green clouds, grazing like tiny pink cattle. Baleen whales track the krill clouds by sonar, carving walls of bubbles to corral them. When whales defecate near the surface, iron-rich waste sparks secondary blooms a vividly named whale pump that fertilizes more phytoplankton and pulls yet more carbon from the air. In this way, the motion of great blue giants pairs with the flicker of cells, no thicker than a strand of hair, to modulate planetary chemistry. Slide southward now, to the Agulhas Current, a roaring river, hugging Africa's southeast flank. As it barrels west at highway speeds, eddies peel from its flankworm, spinning rings the size of Connecticut. These rings slip into the colder South Atlantic, injecting salt and heat that fortify the Atlantic meridional overturning circulation. The very conveyor whose northern branch tempers European winters. When an Agulhas ring collapses, remote sensors record a hiccup in Atlantic salinity hundreds of miles away. A weather forecast for Spain may be whispered first by eddies curling off Madagascar. Not all current tales hinge on warmth. The mind tends to picture tropical blues and sunlit shallows, yet chilling cold is the other half of the engine's stroke. In the Ross Sea, katabatic winds pour off Antarctica's white plateau, freezing ocean spray midair. Sea ice forms, excluding salt as it crystallizes. The leftover brine grows so dense, it cascades downslope in gushing torrents called brine plumes, some plunging 3 vertical miles before fanning across the abyssal plain. Where those plumes spill over deep ridges, bottom water flows north oxygen-laden, -1.8 degrees Celsius, so clear and sterile that only ghostly sea cucumbers patrol its silence. Thousands of kilometers away, corals on Atlantic seamounts fan delicate polyps into that same flow, depending on its steady chill, even as surface temperatures climb year by year. Pause for a moment to recognize how intimately our daily lives ride the backs of such currents. Refrigerated produce from Chile, shipped north across the Humboldt Current, arrives crisp in Canadian supermarkets because the cold air above the current quells microbial growth on deck. Fiber optic cables, streaming beneath the Gulf Stream, must be armored and precisely tensioned to survive its ceaseless tug. Even the humble weather report in a smartphone app relies on sea surface temperature readings plugged into numerical models, where swirling eddies adjust probability distributions of rain 10 days hence. During World War II, Allied meteorologists studying Atlantic convoys realized that storms often brewed where warm and cold currents collided, long before barometers on deck dipped. Their insights led to early warning networks that saved ships from U-boat ambushes cloaked in fog. Today, drone sailboats, armed with LiDAR, skim those same convergence zones, mapping humidity jumps that will seed tomorrow's hurricanes. Shouldering through history, consider the voyage of the HMS Challenger in the 1870s. Its crew trawled weighted nets 4 miles deep, hauling up manganese nodules and gelatinous creatures never before seen. Their thermometers recorded a triplet of cold layers in the Atlantic, each colder and fresher than the one above, evidence of episodic pulses in deepwater formation. Those Victorian observations underpin modern reconstructions of century-scale current variability. Glass thermometers, carefully rammed into wooden holders, still lie archived beside digital Argo profiles, bridging eras in a shared language of temperature and salt. Meanwhile, human influence presses its thumb on the scales. Burning coal, gas, and oil thickens the blanket of greenhouse gases, trapping extra heat that one day sinks into the sea. 90% of excess heat from anthropogenic warming now resides in upper ocean layers. Thermal expansion alone has raised average sea level by centimeters. Warmer water simply occupies more volume, but deeper consequences lurk. As heat diffuses downward, density gradients shift, winds shift, and the jigsaw of currents rearranges. Computer simulations suggest that if the Atlantic conveyor slows substantially, tropical rainfall belts may migrate, Indian monsoons may hesitate, and North Atlantic hurricanes might pinch closer to coasts than before. Yet models also reveal potential feedbacks that soften blows. Stronger southern ocean winds energized by the same warming could enhance upwelling, allowing the deep ocean to absorb more carbon for decades, buying humanity time. Whether that boon manifests depends on aerosol pollution trajectories, volcanic eruptions, forest regrowth, and countless other variables. In climate science, as in the sea, every push begets counterpushes. Predicting the net path of currents 50 years hence demands supercomputers crunching equations etched in nested grids, millions of points wide. If you're still listening, eyelids heavier yet mind awake, you share a moment with many others riding the same lull of curiosity. Somewhere, perhaps in New Zealand's pre-dawn hush, or Brazil's humid dusk, another listener imagines these water highways swirling in darkness. Waves outside their window crash in, patterns tuned by identical physics. The thought underscores a hidden fraternity. Though currents wind unseen, they stitch together strangers with a thread of turning water. Let us hover briefly inside a laboratory cold room, where seawater samples await analysis. A scientist spins them in a centrifuge to separate living cells from dissolved salts. On a slide under ultraviolet light, individual plankton gleam emerald tiny suns, each holding traces of nitrogen isotopes that betray where they grew. From such flecks, researchers map the life history of water masses. This one fed by upwelling near Peru. That one formed under Arctic pack ice. Chemical forensics at the scale of single cells allows climatologists to reconstruct routes of currents centuries past, calibrating models with surprising accuracy. While instruments unveil stories, indigenous seafarers have read currents for millennia by feel alone. Polynesian navigators sensed subtle changes in swell direction, reflected wavelets bending around unseen islands hundreds of miles away. Inuit hunters read the slush texture along flow lines between flows to forecast wind shifts. Even the smell of seaweed or a faint uptick in water temperature might tell an experienced fisherman where a warm eddy brushes a cold shelf, promising tuna under circling birds. Before tonight's reflections settle quiet, frame one last mental image. Earth at night, as photographed from orbit, city lights scattering golden dust across continents. Beneath those lights flows an even vaster, darker illumination, rings of phosphorescent plankton shimmering under moonbeams where currents converge. Each spark is a single Dinoff flagellate, swirling the dark with chemical light, echoing starlight absorbed long ago. The surface of the sea glows, not because cities shine down, but because life thrums upward, energized by nutrients lifted from the deep by persistent, tireless motion. Let that vision drift quietly at the back of your thoughts as your breathing steadies, the room darkens, and awareness softens around the edges. The ocean's hidden highways roll on, night and day, age after age, whether eyes watch or eyelids close. Breathe in the faint hush of a pre-storm calm, the kind of silence that spreads across coastal marshes when even the herons pause, then let the air drift out as steadily as a tide turning at slack water. That unhurried breath anchors you as we slide from the broad gyres we have already traced into deeper corridors, where the ocean keeps its sprawling chemical ledger, balancing carbon, nutrients, and heat with the patience of a stone monastery. Imagine lowering yourself through layers of twilight water, each darker than the last, until the final trace of daylight surrenders to velvet black. All around, translucent flakes descend in gentle spirals. Oceanographers call this perpetual drizzle marine snow. A flurry of diatom shards, fish scales, jelly fragments, grains of prairie dust, and soot from distant wildfires. Each fleck is lighter than a fingernail clipping, yet together they fall in such abundance that they blanket the abyssal plain with a whispering snowfall all year long. Given centuries, these whispers compress into ooze, and the ooze becomes a library floor where every millimeter preserves whether long vanished and skies no living soul has seen. Before marine snow can gather, currents must stage an elaborate dance of sinking chills and rising nutrients. Along continental margins, west-blowing winds peel surface water offshore, and deep cold nutrient-rich water rushes upward to replace it. Picture the coast of Central California at dawn. Fog drapes the headlands like gauze, and the sea below swirls jade and almond milk where diatom blooms thrive on iron lifted from canyon floors. Viewed from a cliff, those pale spirals look like the marbling in hand-pulled paper. Within days, cloud-like blooms feed krill so thick that blue whales can locate them by sound. Seabirds plunge beak first into silvery bait balls. Sea lions bark over frenzied herring. Fishing crews haul nets, twanging with sardines that glint like hammered tin, while upwelling zones feed coastal life. Their mirror image unfolds thousands of miles away beneath polar skies. Their winter winds roar unchecked, raking warmth from slate-gray waves until the surface thickens and brines. As seawater begins to freeze, pure ice crystals reject salt, leaving behind heavier brine that sinks in thunderous plumes 2 miles deep. Oceanographers label this deep convection. Yet the phrase masks drama. Pillars of water denser than granite tumble downward, roaring so loudly that hydrophones anchored on the seabed record their bass rumble for weeks. Every plunge drags surface gases into the abyss, oxygen to ventilate far-flung trenches, carbon dioxide breathed by factories and forests alike. Now, allow your shoulders to unclench and your jaw to loosen. Feel tension drop like one of those brine plumes, leaving upper layers calm and receptive. With just that brief invitation, body and mind find a shared stillness, mirroring the sea once turbulence settles in the dark zones beneath. The sinking water flows south, along submarine ridges, beneath equatorial latitudes, and eventually beneath the encircling ice gates of the Southern Ocean. There it rises again, not in a single geyser but in sheets, lifted by howling westerly winds. Where ancient water meets sunlight, it releases nitrogen, phosphorus, and iron collected on its pilgrimage. Microscopic plants bloom in swirling turquoise meadows visible from orbit. Each unicellular alchemist fixes carbon dioxide into sugar and liberates oxygen that will drift on jet stream winds, eventually filling lungs on mountaintops and city streets. Ecologists call this process of biological carbon transfer the ocean's biological pump, likening it to a billion miniature elevators. Carbon dioxide steps aboard near the surface. Gravity lowers the cab into darkness, and over years, the payload locks away in sediment or carbonate. In a typical orbit around the Sun, this pump swallows roughly 10 billion metric tons of carbon dioxide, a quarter of what humanity releases by burning oil, coal, and gas. Without it, atmospheric carbon dioxide would climb even faster, and Earth's fever would mount in step. Alongside the biological pump hums a quieter machine known as the solubility pump. Chilled water can dissolve more carbon dioxide than warm water, just as cold club soda retains fizz better than a soda left in the sun. At high latitudes where air temperatures hover below the freezing point of water, seas gulp carbon dioxide, like a sponge. When that chilled water sinks during deep convection, it escorts the dissolved gas into the abyss, storing it beyond the reach of wind and light for hundreds of years. Over such epochs, some of the gas reacts with calcium to form chalky nodules that stud the mud like scattered pearls. Only after a millennium might remnants of today's exhaust emerge. Again in a distant upwelling plume. All seems finely tuned, yet the balance teeters. As anthropogenic emissions climb, extra carbon dioxide dissolves into surface layers, forming carbonic acid that nudges the ocean's pH downward. A shift of even 1/10 on the pH scale signals a 30% increase in acidity. For creatures that build shells from calcium carbonate, sea butterflies, sea angels, coral polyps, this is like raising rent on every molecule they need to build homes. Along the Pacific Northwest, oyster hatcheries now pre-treat incoming seawater with ground limestone to buffer acidity before introducing delicate larvae. Their makeshift remedy foreshadows challenges awaiting reefs, crustaceans, and perhaps entire food webs. Acidification does not spread uniformly. Currents become couriers, delivering pockets of corrosive water into unexpected bays. The California current, which drapes the west coast in fog lustrous and cold, periodically draws acidic deep water to the surface. In some summers, that water nudges the pH low enough that sea urchin larvae fail to form proper spines. In these same epochs, kelp forests along the coast shrink, while invasive algae, tolerant of acid, stretch into vacant space. Temperature anomalies ride currents too. Every 2+ years, winds slacken across the equatorial Pacific, and the warm tongue of El Niño glides east. The Humboldt currents cool upwelling sputters, surface temperatures climb. Anchovy populations scatter into deeper, cooler layers. Seabirds abandon nests. Fishermen confront nearly empty nets. Conversely, La Niña strengthens trade winds, invigorates upwelling, and replenishes nutrient pipelines. These oscillations, though natural, now overlay modern warming, pushing highs higher and lows lower. Some years, marine heat waves cook kelp forests in weeks. In others, upwelling plumes draw icy water that stuns tropical snappers seeking new ranges. Currents shape rainfall as well. Over warm ribbons like the Gulf Stream, evaporation ramps up, filling air with moisture. That vapor, carried inland by prevailing winds, condenses into rain, nurturing oaks in Ireland, pines in Norway, and vineyards in coastal France. Above cooler currents, evaporation slows. Low stratus forms but seldom spills rain. Along Patagonia's arid Atlantic edge, sheep ranches rely on dew and fog more than on storm clouds. All because the Falkland current chills the air overhead. These oceanic patterns do not merely set weather, they steer history. Vikings once rode fair winds and the warmth of a robust Gulf Stream to reach Greenland's southwestern fjords, raising sheep and barley. When colder currents reasserted dominance during the onset of the Little Ice Age, pastureland withered, and settlers withdrew. In 1816, Ash from Tambra's eruption shaded the sky and cooled surface waters. Contemporary ship's logs show sea temperatures 2 degrees Fahrenheit lower than average. Cod runs faltered, and New England canneries collapsed, and the same year farmers lost midsummer crops to frost. Today's instruments measure such shifts with exquisite precision. Satellites scan sea surface height to the inch, mapping warm eddies where water piles up. Gliders equipped with oxygen sensors trace subsurface currents in three-dimensional lacework. Moored buoys sample acidity, salinity, temperature, and dissolved oxygen every few minutes, delivering continuous streams of data to supercomputers. Modelers simulate scenarios. Suppose Greenland's ice sheet melts at twice the present rate. How will freshwater plumes alter sinking in the North Atlantic? Or imagine stronger circumpolar winds spin up deeper, upwelling, drawing more carbon dioxide out of the air. Will that buffer warming, even as acidity deepens? If the forecast feels uncertain, find steadiness in one deep breath. Draw cool air to your diaphragm, feel ribs expand, like the wooden ribs of a harp, then let the exhale glide free. Salinity, temperature, and wind each rise and fall in measured counterpoint, and so can your breath. Meanwhile, adaptation sprinkles coastlines with ingenuity. Conservationists restore seagrass meadows, where gentle currents deposit silt, capturing carbon and damping wave energy. Engineers test underwater turbines in the swift Gulf Stream, spinning tidal currents into power without combustion. Even small communities lean on current knowledge. An Alaska village, once pinned by shorefast ice, now faces open water in winter. Residents have altered fishing calendars to match salmon drawn northward by shifting thermal fronts. For millennia, indigenous seafarers have tuned themselves to these flows. Polynesian navigators sensed interference patterns between swells to locate islands beyond the horizon. Inuit hunters read types of slush between flows to anticipate shifting leads. Indonesian fishers still track subtle color changes where cooler upwelling meets warm surface flow, a sure sign of tuna prowling below. Their lexicon of ripples, tastes, and scents comprises an oral cartography paralleling modern satellite grids. Envision Earth on a moonless night from orbit. Cities gleam amber across continents, yet dimmer luminance flickers over the oceans. That glow is bioluminescent plankton waking in the turbulence where currents meet. Each cell pulsing sapphire and emerald like a living Morse code. Astronauts describe rivers of light snaking through darkness, marking invisible boundaries where warm and cold water intersect, where nutrients rise and predators feed, as your breathing steadies and eyelids grow heavy. Keep that image close. Invisible currents, guiding glowing filaments of life, writing patterns in darkness. Whatever changes lie ahead, the sea's ledger will keep balancing entries of heat and salt, carbon dioxide and oxygen, life and dissolution. And so we drift onward, following those tallied lines toward other elements of this story: rings of swirling eddies, rivers of vapor aloft, and the way ocean motion reaches even the deepest bedrock of the continents. Warm and cold ribbons still coiled beneath the surface like living brushstrokes, each swipe altering wind, rain, and even the chemistry of clouds. Follow one of those ribbons landward, and you arrive at coasts where moving water meets fixed earth places, where currents slow just long enough to sculpt bays, feed wetlands, and carve channels that decide whether villages flourish or are claimed by salt. Our journey now threads along shorelines, through straits, and under polar ice shelves, tracing how boundary currents and tides turn the ocean's grand, sweeping motions into local stories of soil, food, and shelter. Imagine standing knee-deep in the shade of a mangrove forest on the Andaman coast. The tangled roots feel like a living maze, each arch catching silt that arrives on every incoming tide. That tide is fed by the East Indian coastal current, itself nourished by a loop of the larger monsoon gyre. When the summer monsoon blows, from sea to land, the current flows north, pressing warm water against deltas, raising sea level a finger's breadth. In winter, the wind reverses, and the current turns south, lowering coastal water by the same subtle margin. Yet that margin is enough. During the northerly phase, suspended mud settles among mangrove roots, expanding the forest floor. During the southerly phase, seedlings breathe air newly exposed. Over years, the forest creeps outward, building a green barricade that softens storm surges and siphons carbon dioxide from the air faster than most rainforests. Each prop root becomes a vault where carbon, once floating free in the atmosphere, now rests locked in woody tissue and peaty soil, safe from lightning strike or sawmill. Shift your view several thousand miles west to the Red Sea's narrow waistline. There are liquid jet-fast, salty, shimmering with heat threads, the Straits of Tehran and the Strait of Bab el-Mandeb. Oceanographers call it an exchange flow. Lighter, less salty Indian Ocean water pours in at the surface, while heavier, supersaline Red Sea water escapes at depth like an exhaling lung. Coral reefs hinging on that exchange have evolved to tolerate some of the warmest, saltiest surface water on Earth. They might become a genetic ark for future reefs as global temperatures climb. But the exchange also governs local weather. When export of deep saline water slackens during a strong El Niño year, surface layers freshen slightly, altering evaporation and nudging regional rainbelts. Farmers in the highlands of Ethiopia study decades of rainfall journals and see the fingerprints of that strait, proof that a 30-kilometer choke point can influence harvests thousands of meters up a mountain. Further north, picture the Skagerrak between Denmark and Norway, a meeting ground for brackish Baltic outflow and salt-laden Atlantic influx. Where the two layers slide over each other, internal waves ripple along their interface like silk on glass. Although invisible from shore, these subsurface waves rise tens of meters and stretch 4 kilometers, creating corridors that mix nutrients upward. Fishermen in tiny wooden boats have long noticed that cod cluster along invisible lines on calm nights. Modern sonar now maps those very lines as standing waves rolling beneath the hull. Generations of local lore, once dismissed as myth, align precisely with LiDAR readings from planes slicing the twilight sky. Take a slow breath, letting shoulders drift down as if they were settling sediment grains. Feel tensions sink, leaving upper layers of thought clear enough for new currents of imagination to flow. Straits also gate the progression of tidal rapids, places where daily tides squeeze through rocky narrows, spinning water into lenses of foam. The most famous may be Saltstraumen in Norway, where each 6-hour pulse forces 400 million cubic meters of seawater through a channel just 150 meters wide. The result is a maelstrom of whirlpools and standing waves tall enough to toss small fishing boats like leaves. Beneath that fury, dense bottom water scours the fjord floor, carving potholes and grooves that become refuges for cold-water corals and crustaceans. Divers who brave the subsiding slack feel heat shimmering in layers. Warm Gulf Stream remnants on top, Arctic runoff below. The vertical mixing keeps nutrients in motion and sustains enormous schools of coalfish that feed both sea eagles above and coastal families ashore. Across the globe, the narrow pass between British Columbia's Vancouver Island and the mainland funnels similar quantities of water through Seymour Narrows. There, a single submerged rock, named Ripple Rock, once caused more shipwrecks than any reef on the Pacific coast. In 1958, engineers drilled tunnels under the seafloor and packed them with explosives, 42 metric tons of dynamite. The blast cleaved off the rock's twin peaks, quieting the Narrows just enough for safe passage. Yet the same tidal surge still races at up to 15 knots, driving underwater turbines today that generate renewable electricity for island communities. Engineers map the tidal current's exact speed and timing against the lunar cycle, ensuring each turbine blade slices through peak flow at just the right angle, converting the sea's ceaseless breathing into light for nighttime. Reading. Move now to polar latitudes, where tidal forces meet ice. The Ross Sea's ice shelf undulates by more than a meter twice each day, under the pull of the moon. That rise and fall pumps seawater through fractures at the shelf's grounding line, ventilating caverns where fish with antifreeze proteins drift in near darkness. When high tide forces a slug of slightly warmer water into those cavities, it melts the base ever so slightly, freshening the outflowing plume. Scientists deploying autonomous ice-penetrating drones have traced that loop and measured pockets of 20-degree Fahrenheit water-licking glacier roots. The meltwater then caps the shelf with a layer of fresher, lighter water, altering the sea ice's growth and the travel routes of emperor penguins that rely on stable platforms for breeding. Currents press inland as groundwater, too. Along Florida's Gulf Coast, Warm loop current, water increases evaporation, adding humidity to breezes that sweep over karst landscapes riddled with sinkholes. Moisture seeps underground, recharging the Floridan aquifer, and emerging as crystal-clear springs from which manatees squeeze refuge during chilly winters. Without the warm currents, humid push, spring flow would dwindle, aquifer recharge would slow, and saltwater intrusion would creep inland. Thus, a current hundreds of kilometers offshore guarantees fresh water that nurtures citrus groves and fills backyard glasses, while the connections between offshore flow and inland life amaze. They also caution. If the loop current lingers anomalously close to shore, warm water can feed hurricanes, enabling rapid intensification and explosive deepening every forecaster dreads. When Hurricane Michael roared across a warm core eddy in 2018, its wind speed leaped 35 miles per hour in a single day before slamming into the Florida Panhandle. Researchers later mapped sea surface height anomalies, revealing the eddy's signature bulge, as sure as a fingerprint in gelatin. Internal tides, the deep ocean counterpart of surface tides, also channel energy shoreward, generated as the lunar pole drags dense layers over seafloor ridges. These internal waves can travel hundreds of miles before breaking on continental slopes. When they do, they loft cold water, rich with iron, toward the surface around midnight, especially near Hawaii's Kona coast. Octopus fishers time their nets for that pulse, because small crustaceans riding internal bores lure the armed hunters into view. Consider now the Mediterranean's storied Strait of Messina, reputed haunt of mythical Scylla and Charybdis. Rapid tides interacting with opposing winds spawn standing waves and whirlpools that shimmer silver under Sicilian moonlight. Fishermen long ago learned that swordfish loiter along those mixing lines at dawn, waiting for disoriented sardines spit out from vortices. Modern hydrocaustic surveys confirm swordfish density peaks exactly where myth placed Montsusa. Tidy alignment of folklore and fluid dynamics. Take another unhurried breathlet, air slip in cool, and depart warm. For a moment, sense your heartbeat in your eardrums, like faint surf echoing through shells. That single awareness moment offers the same kind of calibration ocean pilots once relied on, aligning rhythmic thumps of heart to rhythmic pulses of tide. Currents continue beneath seismic quiet zones, too. In the western Pacific, the Mariana Trench hosts a deep current lane where water colder than 32 degrees Fahrenheit slides from the North Pacific into the Philippine Sea basin, because pressure prevents freezing. The water remains liquid, yet dense as lead. Sediment cores from trench walls show chutes of coarse sand transported downward by episodic turbidity currents that couple to that dense flow. Each chute buries everything in its path: organic matter, microplastics, the occasional deep-sea amphipod trapping carbon for eons under skyscrapers of silt, looking upward again. River plumes add their own signature, traced far offshore by ocean color sensors. When the Amazon floods, it spews a tongue of tannin-stained water 500 miles into the Atlantic, layering over salty surface water like milk over coffee. That lens mutates local stratification, calming waves and fueling sargassum blooms, later swept into the Caribbean. Tourism boards track satellite chlorophyll maps to anticipate when these floating seaweed mats will beach on resort shores. While coral nurseries rejoiced, the same mats can shade bleached reefs, trimming summer heat by a needed degree. Throughout these varied examples, one truth repeats: the ocean's grand loops show up as local particulars routes catching silt, turbines slicing tide, vineyards measuring fog, insurance companies adjusting storm premiums by fractions of a degree. Each subtle shift begins with energy drawn from the sun, transferred by wind to water, and moved along curving coasts, through throttled narrows, or under shifting ice. Then it takes an earthly form: a school of salmon, an acre of salt marsh, a hint of mango sweetness carried inland on humid night air. Allow your eyelids to soften further. There is no need to catalog every fact. Like waves overlapping on a quiet lagoon, details can mingle until only a gentle rocking sensation remains. What matters is the larger pattern, a symphony in which each instrumentary ring, tidal bore, groundwater lens plays a line that merges into the next dot as the symphony continues. We will soon meet yet subtler notes, the ripples of internal waves bending light like underwater mirages, and the silent highways of deep sound channels through which whales send songs across whole ocean basins. Together they suggest that the sea is not merely a stage where drama takes place, but an active musician, composing water into rhythms that set tempo for life on every continent. And so the current chapter settles into calm, leaving space for the next movement in our exploration to gently rise when you are ready to follow. Beneath every rolling swell lies another world of waves, moving silently through darkness, shifting layers that only instruments or creatures with otherworldly senses can detect, while the surface of the ocean shows ripples sculpted by wind or passing ships. The interior hosts giants called internal waves, slow undulations that travel along density boundaries, much the way breezes glide over rolling hills. Yet here the hills are invisible gradients of heat and salinity, and the breezes are nudges of gravity tugging against slight imbalances. Think of the ocean as a vast parfait, warm light water lingering on top, cooler, heavier layers below, and at their meeting place, a hidden seam where motion gathers strength. To imagine an internal wave, place a thin sheet of silk atop a heavier velvet curtain, and tap the edge. A ripple glides across the seam, while the fabric above scarcely stirs. In the ocean, tides provide the tap. When the moon pulls at seawater, surface tides rise a yard or two, easily seen from docks. But below, the same force drags dense layers over rugged seafloor ridges, setting off underwater waves that can tower hundreds of feet in amplitude, yet leave the surface almost flat. Submariners learn to ride those stealth ridges. A vessel buoyant in warm water may suddenly sink several fathoms, passing into a cold core trough, as if descending an unseen hill. One of the grandest internal wave arenas curls around the Philippine archipelago. Their tides force warm equatorial water through the Straits of Surigao and San Bernardino. As the flow meets steep sills, internal waves radiate westward into the South China Sea, in packets so immense that satellites spot their wake. Bands of rough and smooth surface water marked by alternating light and dark stripes. Longline fishermen study those stripes and don light dark lines, hint where internal crests compress the surface and gather plankton, and where small tuna spiral beneath. Scientists deploy instruments called line moorings, arrays of sensors strung like bead necklaces from buoy to anchor, to watch temperature and salinity rise and fall as wave after wave rolls. Past in hush and shadow, internal waves are not only curiosities, they redistribute heat and nutrients. As a wave crest lifts cold water toward sunlight, it ferries iron and nitrate into photic zones, sparking blooms that stain the sea jade. When the trough sinks, it drags oxygen-rich surface water toward depths starved of breath. Over shelf breaks, internal waves sometimes break, much like surf tipping into foam. The break injects turbulence, mixing layers that would otherwise remain stratified. Physical oceanographers liken the process to stirring cream into coffee, but gently, over days rather than seconds, ensuring life at depth receives an intermittent rations of warmth and food. Farther south, beneath the equatorial Atlantic, a colossal internal tide forms, where the mid-Atlantic ridge rises like a buried mountain chain. Each lunar pool drives dense water upslope. As it overshoots the crest, the water sloshes down the far side, generating waves that propagate east and west for hundreds of miles. They reach Amazon plume waters rich with silt, lifting sediment into mid-depth layers where iron becomes available to diatoms swirling offshore. Those diatoms feed zooplankton that in turn nourish juvenile fish, pouring out of estuaries. Thus a mountain no person will ever see, touched by a moon no hand can grasp, fertilizes a food chain that ends on dinner plates half a continent away. Pause here and allow one slow, unforced breath. Inhale gently, feeling the ribcage expand, like a bellows, then release the air in a calm stream, sensing shoulders relax. Let that single breath mirror the rising crest of an internal wave, lifting calm from deeper layers to the surface of awareness, then letting it glide back again without effort. Internal motions guide sound as much as nutrients. There exists in the ocean a band called the Deep Sound Channel, a natural acoustic waveguide that arcs around the planet like a whispering gallery. Near a depth of roughly 3,000 feet, where cold compressive pressure meets a remnant of warmer water, Sound speed reaches a minimum. A noise made here, perhaps the click of a beaked whale, or the ping of a research sonar, bounces between layers and travels thousands of miles with little loss. During the early Cold War, naval engineers launched low-frequency chirps into this channel and captured faint echoes half an ocean away, hoping to track distant submarines. Marine mammal biologists later realized whales had mastered the trick long before hydrophones existed. A blue whale off the Azores may bellow and have her moan heard clear as a bell in the Caribbean, the call riding the channel in repeating arcs. The sound channel flexes with seasons. When warmer upper layers deepen in summer, the channel sinks like a lowered corridor. In winter, it rises. Internal tides wrinkle its ceiling and floor, bending sound into lenses that mariners call convergence zones, places where distant echoes briefly sharpen. Sonar officers watch for those lenses, the way lighthouses watch for shoals, steering signals around pockets that might hide their own vessel or mask a lost sensor at depth. Researchers studying under-ice topography in the Arctic now exploit similar bending, sending coded chirps that ricochet under the frozen lid, mapping roughness where warmer Atlantic water nibbles the ice from below. Sound also turns into heat under special conditions. When storm waves exceed a certain height, whitecaps inject bubbles that scatter noise downward. The scattered sound sinks, releasing small pulses of energy that warm microlayers by a fraction of a degree. Over vast storms, the heating becomes measurable, a feedback where the roar of the wind literally warms the sea. It churns. Internal waves modulate bubble layers, thickening them along crests and thinning them in troughs, so the heating flickers in stripes. A Morse code that satellites would read if their infrared sensors were fine enough. Along continental slopes, internal waves shape life, seemingly adapted to motion itself. Thousands of feet deep off Monterey Canyon, researchers using remotely operated vehicles filmed fields of bamboo coral gently swaying in currents driven by internal tides. The corals open and close polyps in rhythm with the passing wave phase, capturing suspended detritus as it pulses upward and down. Every 6 hours they feast. Every 6 hours they rest. Growth rings and coral stalks encode that rhythm the way. Tree rings mark rainy, season slow, steady bands when internal tides lull. Thicker, denser bands when tides intensify under rare alignments of sun and moon. Where internal motion reaches shallows, swimmers may experience it without knowing. On Australia's continental shelf, nighttime beachgoers sometimes report warm pulses of water surging waist-high, then slipping away moments later. Thermal imaging. Drones have traced those surges to internal bores climbing the shelf face, spilling warm interior water over cooler shallows under starlight. Surfers have learned that such bores precede glassy dawn conditions. The mixing quells small chop, rendering the sea smooth as poured mercury. Just as sunrise paints the horizon, the diversity of internal features invites technological mimicry. Engineers designing high-efficiency heat exchangers have studied how internal tides enhance mixing without external stirring. New designs mimic layered wave rollers, using baffles shaped like seafloor ridges to draw cold and warm fluids together, with minimal energy. Elsewhere, acoustic communication networks piggyback on the deep sound channel, allowing deep-sea sensors to relay data hundreds of miles, hopping signals via drifting floats that surface occasionally to transmit findings to satellites. Internal waves even move sediments in ways that rewrite coastlines. The Persian Gulf's Basra Ridge hosts such waves tuned to seasonal winds. In summer they slide fine sand toward Kuwait's shore, extending beaches year by year. In winter, the pattern reverses, scouring dunes into submarine fans. Coastal engineers mine century-old maps, comparing old sandbar outlines to modern sonar, discovering internal tide fingerprints in subtle curve, parallels no storm surge line would leave. Zoom outward and see internal tides as a pulse blurred across. The whole planet, perhaps 10 times more energetic than all the world's rivers combined. Yet the waves remain invisible to most eyes, sensed mostly by satellite altimeters that pick up faint bumps a centimeter high and tens of miles long. Transform that into perspective. A 1 centimeter deflection over 30 miles reveals a fluid mountain, its slopes hosting fish, scattering sound, fertilizing surface water, and warming microlayers. Science advances by turning tiny signals into giant insights. One gentle thought may linger. If such colossal machinery hides in plain sight, what other rhythms hum beneath daily perception? Migrating fish sense faint magnetic pulses, guided by internal motion. Seabirds smell dimethyl sulfide plumes, rising from phytoplankton stirred by internal waves. Even drifting plastic finds pathways shaped by hidden shear, converging into visible from space. The mundane and the wondrous ride, the same unseen rails, catch another breath, slower than the last. Feel it lift and fall, like the heave of water, meeting an internal tide cliff, then settling. That simple loop of air echoes loops of water that never cease, whether we notice or sleep. From waves of silence to rivers of sound, from nutrient elevators to acoustic highways, the ocean's interior pulses extend influence far beyond blue horizons. They govern whale dialogues spanning hemispheres, shape weather signals inside models that predict next week's rain, and even inspire new forms of energy harvesting we may rely on in years to come. The deeper we listen, the more clearly these hidden drums reveal a steady cadence connecting equator to pole, dawn to midnight, breath to breath. And so the journey carries onward, each gentle current leading to another layer of marvels waiting beneath the next moonlit ripple. Currents shape the ocean's skeleton as surely as they sculpt its skin, chipping canyons into the seabed, sanding plateaus, and piling sediments into shifting deltas that rise or retreat with every surge of moving water. Follow one such current down the northern flank of the mid-Atlantic ridge, and you discover a procession of hydrothermal chimneys, each belching mineral-rich water, hot enough to blacken steel, yet surrounded by sub-zero seawater only arm lengths away. The chemistry that explodes from these vents would poison a coral reef, but here it seeds life in abundance. Tube worms, 3 feet long, bloom like ivory lilies. Blind shrimp cluster where heat meets dark. Archaea, with enzymes impervious to scalding temperatures, split hydrogen sulfide into energy. Their energy source is not the sun, but the furnace of Earth itself, stoked by currents that channel the vent water into upward plumes, cooling it just enough for living membranes to survive. Vent plumes rise until they reach density levels matching the ambient ocean, then spread laterally in thick, smoke-colored layers. Internal tides catch those layers, folding them like dough, dispersing dissolved iron thousands of miles. Far downstream, that iron drifts into surface waters, starved of micronutrients. There it seeds blooms of diatoms that, in turn, draw down more carbon dioxide. In a real sense, the respiration of tube worms, in absolute darkness, influences the greenhouse gas levels in air, breathed by swifts slicing across an autumn sky. The scale of such linkage invites both awe and humility. Every drifting feather on every migratory bird owes a trace of its mass to chemical exchanges begun in blackness. 2 miles below, currents carve topography in quieter ways, too. Along the Argentine continental slope, turbidity currents underwater. Avalanches rush down canyons, scouring troughs deeper each century. Seismographs often register their low rumble following major storms or earthquakes. Marine geologists lower camera sleds afterward, revealing new furrows cut through soft mud, their walls lined with freshly exposed fossils. Those slides create sediment fans 500 miles long where nutrients accumulate and deep water fish find both shelter and prey. Each fan resembles a grand mural, its layers recording floods, landslides, and dust plumes from Patagonian deserts carried out to sea by wind. By reading subtle shifts in grain size and chemistry across the fan, scientists trace climatic rises and falls, stretching back beyond written history. Tides, currents, and gravity also build deltas, the fertile ladders between river and sea. The Mekong Delta owes its shape to a delicate PA. The dew between the river's load of silt and the coastal current that sweeps west along Vietnam's shore. When seasonal floods surge, mud outruns the current and accumulates as new land, where rice farmers soon stake fields. During dry spells, the coastal current gnaws edges of that same land, carrying clay back to sea and dropping it in mangrove forests farther downshore. Walk the levee past a stilthouse village, and you see storm debris perched on roofs, 4 meters above high tide. stand in the same spot 10 years later, and the levee has migrated seaward, extended by fresh alluvium. Each generation rebuilds. Homes on new ground, an unspoken covenant with the current that land and livelihood remain mobile. Across the Pacific, the Columbia River plume paints the sea a translucent jade for 50 miles beyond the bar. Northwest winds press that plume south in summer, fanning a cold, nutrient-rich filament along the Oregon shelf. Salmon smolts hitchhike on the filament, their bodies turning from river silver to ocean chrome as they acclimate. Fisheries biologists tag finger-sized juveniles in estuaries, then recapture adults 3 years later, discovering that return rates rise sharply in years when winds and currents align to build the filament swiftly. A minor alteration, wind shifting 5 degrees, or current easing by half a knot, can ripple into a multi-million-dollar swing in salmon harvests. Thus, menus inland feature grilled Chinook, or bland substitutes depending on the barely audible arguments of water and wind months earlier. Pause and invite a gentle inhale, letting the breath move through ribs like a tide through stone arches. Then release it slowly as sand drains between fingertips. That single measured breath matches the patient cadence with which currents build and erase, assemble and disperse, always moving, yet never hurried. Not all seafloor work is slow. At tectonic boundaries, currents meet seismic upheaval in sudden convulsions. An undersea landslide on the Norwegian margin 1,000 years ago unleashed a turbidity current that raced across the North Atlantic floor at 70 miles per hour, uprooting benthic communities and leaving a 30-foot thick blanket of sediment along its path. Core samples show a sharp layer of pebbles resting on fine clay, evidence of the slide's tremendous force. Computer models now suggest the turbidity surge even triggered a tsunami that left sediment ripples inside Scottish fjords. Eddies born of such cataclysmic flows stir deeper layers for decades afterward, redistributing heat and oxygen like invisible chisels sculpting the abyss. Currents influence seismicity in subtler ways, too. Seasonal changes in water mass loading flex ocean floors, modulating the stress on faults. Along the western Aleutians, researchers have correlated microquake rates with oscillations in the subpolar gyre. When winter winds deepen the subpolar front, adding water mass above locked faults, tremor frequency changes, tapping out cryptic patterns. The energy release is tiny, but it offers clues about fault lubrication that may refine. Tsunami risk assessments. Geothermal energy harvesters eye these same margins, using closed-loop heat exchangers planted in vent-rich crust. Prototypes already power small monitoring stations with no combustion whatsoever, converting the ocean's internal furnace directly to electricity. Engineers model local currents to optimize vent capture without cooling delicate microbe colonies that form the base of unique ecosystems. Balance is essential. Draw too much heat, the vent fauna suffer. Draw too little, sensors starve of power. Marine conservationists collaborate with engineers in unprecedented alliances, mapping safe operating envelopes through a synergy of fluid dynamics, biology, and ethics. Along continental shelves, kelp forests illustrate another mode of current-driven architecture. In Western Australia, the Leuven Current sweeps warm water southward, a rarity among eastern boundary flows. Its warmth fosters kelp forests at latitudes where such growth would normally perish in cool conditions. But in 2011, a marine heatwave supercharged the current. Waters warmed 3 degrees Celsius above average for weeks, and kelp fronds simply melted. Satellite images tracked a dramatic decline in forest extent, while underwater surveys recorded reef conversions to turf algae. Since then, cooler-than-average years have allowed new kelp patches to rout, but the forest mosaic remains fragmented, a living ledger of current variability. Currents ignite blooms beyond seaweed. Off Namibia, the Benguela Current's upwelling drives diatom explosions so immense that as diatoms die and sink, their decomposition draws oxygen from bottom waters, creating anoxic zones. Sulfate-eating bacteria thrive, producing hydrogen sulfide, gas that can erupt as toxic surface slicks. In 2008, one such slick washed ashore, bleaching seagrass and forcing villagers to flee the pungent smell. Scientists studying radar backscatter found that internal waves, concentrating decaying biomass at the shelf break, triggered the episode. a powerful example of biological, chemical, and physical feedback. Currents also offer natural laboratories for geoengineering experiments. Near volcanic islands, underwater eruptions coat the sea with pumice rafts. These porous stones float and drift with currents for months, hosting communities of barnacles, algae, and even juvenile corals. Oceanographers track rafts using satellite imagery, noting how currents guide them toward or away from coral reefs that might benefit from fresh larvae. Some propose seeding pumice artificially into warming waters, a gentler intervention than controversial iron fertilization schemes. Currents would shepherd pumice swarms, potentially restoring reefs without discharging chemicals. Critics counter that drifting rafts could smother coastal fisheries or alter light penetration. Both sides consult detailed current models for guidance, proving yet again that any solution, bold or cautious, hinges on understanding the sea's conveyor belts. Deep currents and boundary currents even modulate planetary rotation. Water mass redistribution changes Earth's moment of inertia, slightly altering day length. During strong El Niño episodes, equatorial Pacific waters pile eastward, and the planet spins minutely faster fractions of a millisecond, but enough for atomic clock overseers to maintain records of leap seconds. The dance is reciprocal. Winds push currents. Currents shift mass. The rotating Earth responds, and timekeeping laboratories issue bulletins to software engineers, so satellites, power grids, and financial markets remain synchronized with the turning planet. Catch another breath, perhaps slower than the last. Inhale, feeling a quiet stretch across back and shoulders. Exhale, sensing the ebb. Harmony inside mirrors harmonic currents outside. Each oscillation, a subtle exchange of energy and information. Currents move not only water and heat, but stories. Polynesian myths speak of Te Lukuo, Te Mona, the sea's heartbeat, describing alternate pulses of warm and cool waters that govern fish migrations. Archaeological evidence reveals that settlement waves across the Pacific matched intervals when the north equatorial countercurrent strengthened, easing eastward voyages. In medieval Europe, shipping guilds understood that robust easterly currents in the Strait of Gibraltar signaled bumper herring runs in the North Sea months later. Their observations, codified in logbooks and prayers, anticipate relationships modern analysis confirms. Amid modern shipping lanes, currents guide floating plastic into 5 great subtropical GRs. Cleanup ventures launch booms designed to glide slightly faster than the debris they corral, exploiting shear between wind-dragged surface water and deeper returning flows. Success depends on calibrating boom speed to current velocity within a few centimeters per second, else plastic either slips beneath or pushes the boom away. Data collected by drifting tags reveal daily fluctuations that complicate operations. Yet the same data refine climate models, illustrating how local eddies knit into basin-wide motion. In polar realms, currents act as climate sentinels. The West Spitzbergen Current carries warm Atlantic water toward Arctic sea ice. When its flow pulses stronger, winter sea ice thins, walrus herds shift haulout sites, and phytoplankton blooms start earlier under more transparent ice. Indigenous communities note changes in narwhal migration corridors and adjust hunting calendars. Meanwhile, scientists fit moorings with acoustic thermometers that record current speed via sound travel times, creating year-round datasets to calibrate. Satellite altimetry, compromised by polar darkness. Wherever currents touch land, people build. Engineers designing the futuristic Oceanix Busan floating city in South Korea rely on microcurrent mapping to orient modules so tidal shear cleans dock walls naturally, reducing need for anti-fouling paint. Renewable energy planners allocate floating photovoltaic arrays where currents ease but do not stagnate, preventing biofouling and silt buildup. Even underwater wine cellars in the French Mediterranean exploit laminar bottom currents to maintain constant temperature and gentle bottle agitation, said to mellow tannins. Reflect for a quiet moment. The bottle in a collector's cellar, the salmon on a dinner plate, the leaf of lettuce grown in delta silt. All owe existence to water that began moving long before any human plan. Currents connect geology and gastronomy, myth and measurement, microbe and metropolis. turning the phrase huge tapestry from metaphor into map. As eyelids grow heavy, picture those currents not as arrows on charts but as living ribbons, luminous in imagination. See them cascade over continental shelves, swirl through canyons, seep under glaciers, all while bearing heat drawn from the sun and chemicals forged in Earth's crust. Their ceaseless weaving maintains a habitable world, adjusting every dawn and dusk, 2 orbital shifts, volcanic breaths, and now the newfound influence of human enterprise. The ocean listens, balances, and replies in swirl and surge. Our exploration will soon glide toward the fragile edges where currents meet ice tongues 1,000 years old, revealing how the dance of meltwater and salt decides the pace of the coming century. For now, hold the image of invisible rivers drawn in moving light, and let their tranquil persistence guide your own steady drift into the night's deeper calm. The final stretch of our ocean journey brings us to the planet's silent margins, where currents meet ice older than remembered kings and carve decisions into every shoreline. Imagine a white horizon stretching forever, the air so dry it crackles. In your nostrils, beneath this frozen lid flows a narrow vein of comparatively warm salt water, ferried northward by the West Spitzbergen current. It threads under sea ice like a candle's breath beneath parchment, melting from below and glossing the ice with a glassy sheen. When the current pulses stronger, winter sea ice thins. When it weakens, the ice thickens and stray polar bears find firmer footing for their hunts at the opposite pole. The East Greenland current carries shards of ancient ice southward in dignified silence. Some bergs peel off and drift into the North Atlantic, becoming drifting kingdoms that seed cooler surface layers miles from home. Sensor tags on ringed seals reveal how they weave among these white towers, diving to pockets where meltwater caps concentrate, prey. Plankton thrive under the ice's shadow, feeding Arctic cod, which in turn nourish seals and narwhals before the current ferries the last ice crystals into warmer water and dissolves them entirely. Thus, even the life stories of whales link back to how swiftly or slowly a current escorts its icy cargo. Currents at ice margins decide not only the fate of bears and whales, but also the pace of global sea level rise. Take the Pine Island Glacier. In West Antarctica, beneath its shelving tongue, the circumpolar deep water slides in narrow under-ice canyons, carrying heat that once soaked up equatorial sunlight. The water's temperature hovers just 1 degree Celsius above freezing. Yet its saltiness means it is denser than the fresh melt pooled above. That tiny surplus of heat melts the glacier's underbelly from the inside out, thinning the shelf and reducing its buttressing grip. When the shelf retreats, the grounded glacier behind it accelerates, adding fresh water to the sea that will eventually lap higher on tropical beaches. As meltwater spills forward, it makes the surface layer colder and lighter, potentially tamping down local convection and slowing the very current that delivered the heat in the first place. A feedback loop danced in slow motion. Not all feedbacks hasten loss. Around the Antarctic Peninsula, vigorous winds spin the Antarctic circumpolar current faster, encouraging upwelling that brings nutrient-rich deep water into sunlight. Explosions of plankton convert carbon dioxide into organic matter, some of which sinks and buries carbon for centuries, adding a small break to warming. That same plankton also releases compounds that seed cloud droplets, brightening skies and reflecting a fraction more sunlight to space. In this way, the sea can act like a careful accountant, balancing new debits with sudden credits, keeping the climate ledger temporarily in check. While ocean ice dialogues unfold far from most people's windows, subtle messages travel back through the atmosphere. Meltwater freshens surface layers, which form a thin lens that reflects sunlight and chills local air. Storm paths then shift. One depressive swirl detours north, another dives south, and rainfall falls where soybeans grow, instead of where coffee needs shade. Farmers who never smell brine notice fields wilting or greening, unaware that the trigger was a pulse of fresh water bleeding from a distant glacier. Even the hard stone beneath continents is not immune. As ice sheets thin, their great weight lessens, allowing the crust to spring upward like a mattress relieved of a heavy sleeper. That rebound tilts coastlines ever so slightly, changing river slopes and nudging currents that hug the shore. The Amazon plume, the Mississippi outwash, the Mekong silt fennel respond to these tilts, migrating sandbars that then redirect port channels. Engineers rely on annual dredge schedules, timed to the usual pulse of river discharge. Yet in recent decades have found channels shoaling sooner or migrating sideways. Beneath spreadsheets and budget lines, the hidden driver is a slight flex of the crust set in motion by currents warming ice. Take a moment to settle shoulders and jaw. Breathe in as steadily as a polar current slipping under pack ice, then breathe out with equal patience, sensing the body warm like a sheltered lead, pooling against the flow's edge. That quiet pause anchors the mind, letting the ocean's multitudes arrange themselves in orderly layers, heat against salt, fresh against dense, knowledge against wonder. Currents also guide great migrations in the sky. Every spring, Bart Godwits leave New Zealand on a non-stop flight to the Yellow Sea, steering by subtle gradients in sea surface temperature that signal tailwinds above. Meteorologists track those gradients by satellite. A warm tongue here promises an assisting jet. A cool band there predicts headwinds to avoid. The birds, lacking data feeds, still sense the same map, perhaps by smelling dimethyl sulfide rising from plankton blooms, or by feeling low-frequency vibrations carried through air-water boundaries. Their success is testament to how intimately life has tuned itself to the ocean's BRUSH, STROKES. Our instruments refine that tuning into numbers. Ice-penetrating radar drones map under ice channels where warm currents intrude. Moored pressure sensors note millimeter-level rises in sea level when storm-bent currents pile water against coastlines. Data pour into climate models whose grid cells now measure fewer kilometers across than city blocks. Run on supercomputers, these models test future scenarios. What if meltwater from Greenland triples? What if trade winds slacken by 10%? Some simulations show the Atlantic conveyor slowing, nudging Europe toward cooler, wetter winters even as global averages climb. Others suggest Southern Ocean upwelling may absorb more carbon dioxide for decades, briefly masking the fever. Each run is a careful rehearsal of possibility. Communities are beginning to translate those rehearsals into action. Architects in Rotterdam raise entire neighborhoods on floating platforms aligned to tidal channels. Coastal farmers in Bangladesh shift rice varieties to strains tolerant of brackish flooding, trusting that monsoon-delivered freshwater still follows river currents out to sea for part of the year. Sail cargo companies resurrect clipper routes, timing departures to catch eastern trade-wind currents, curbing emissions while delivering coffee and chocolate across oceans at a pace once considered obsolete, but now viewed as elegant resilience. Currents even influence what culture keeps for posterity. Deepwater archaeologists discovered a Phoenician ship 2 miles down in the eastern Mediterranean, preserved in an anoxic eddy where no wood-eating worm survives. The vessel's amphory still held traces of cedar oil scenting the hold, its bronze anchors untarnished. In archives ashore, perfume makers study the residue to recreate scents worn by queens 3,000 years ago. A swirling pocket of luck. Current thus saved a sensory link to ancient trade, reminding us that water can be as generous a librarian as it is a sculptor or destroyer. Not all generosity comes free. Where powerful boundary currents wrap around capes, they chew cliff bases, triggering landslides that topple lighthouses. Chip by chip, the land yields. Insurance models incorporate coastal erosion forecasts guided by satellite altimetry. Rise in regional sea level. A half-knot increase in alongshore current speed. A 2 °F rise in summer wave temperature, all tiny edges adding up to how far the sea will reach. Beneath foundations by the time children, now in grade school, choose careers. Pause for another breath. Long, but light. Feel ribs drift outward, catching air like the last ice flow, catching sunlight in September. Let the exhale slide, slow as meltwater, oozing into glassy tide pools. That breath is a small comfort, mirroring the ocean's own need for pauses times when winds calm. Internal waves rest, and the ledger balances. Through stories of coral, seeded by drifting pumice, plastic gathered in subtropical gyres, and electricity spun by tidal turbines, one theme persists. Currents do not simply transport, they connect. Nothing in the ocean is truly isolated. Each droplet's path threads through countless webs of consequence. A grain of desert dust lands on water, drifts into a North Atlantic bloom, settles through twilight zones, locks carbon in shell, and centuries later resurfaces to sparkle under polar night. That cycle, repeated uncountable times, weaves breathable, air-stable seasons, and the daily bread of billions. And so our exploration draws to its quiet shore. We set out tracing warm gyres, sank with dense plumes, rode invisible rings, listened to underwater tides, and stood beside glaciers, listening for meltwater murmurs. Every horizon we touched curved back into the same truth. Ocean currents shape climates, cultures, coasts, and dreams, all while whispering lullabies that can guide even a restless mind toward rest. If you still have a bit of wakefulness and would like to share, I would be delighted to hear your thoughts in the comments. Where in the world are you watching tonight, and what hour has the tide of time reached where you are? Your notes help this channel's gentle voyages find fellow travelers under far-flung skies. Should these stories of hidden water roads and living currents have soothed your mind or sparked a quiet sense of wonder, please consider liking this video and subscribing to Science of Sleep. Each gesture lifts the channel's little craft on calmer seas, allowing more listeners to drift in peaceful curiosity. For now, let steady breaths mirror the patient roll of the sea beyond memory. May the rhythms of warm and cold ribbons weaving through darkness guide you into deep, easy sleep. Good night, rest well, and drift gently on the ocean's timeless pulse.